Hi everyone, I'm Xuerong and from Tianjin University, and I'm also worked at the City University of Hong Kong. And I will talk about the electrochemical behavior of transient metals in the cathode of energy storage materials. It contains the lithium-ion batteries and zinc batteries. As we know, the electricity from the fossil fuels and other clean energy systems like the solar cells cannot be directly used, especially for the off-grid systems. Therefore, we developed the lithium-ion batteries as energy storage systems to transfer the electricity to be used for daily life and for the electric vehicles. But the lithium-ion batteries has their own disadvantages like the safety and the lower specific energy like this. Therefore, we also developed the metal air batteries that can be used in other special situations. But the cathodes in the lithium-ion batteries and the metal air batteries contains many kinds of transient metals, like in the layered structure and the spinel structure, olivine, and even dissolved rock salt structures. There are many transient metals like the cobalt, nickel, and manganese like this. This is because the transient metals, especially the 3D transient metals, have diverse electronic states and also the electronegativity and other physiochemical properties. And we also can tune the morphology and the phase structure and the stress and strain properties of the materials to tune the local environmental and electrical properties of transient metals. And then we can tune or enhance the battery performance. Therefore, it is important to explain the energy storage mechanism of transient metal in these materials. In our work, we mainly focus on preparation of these materials, especially the transient metal oxides, sulfates, and selenites. And we use chemical processing and also the ball milling methods. And then we prepare the zinc batteries and the lithium batteries and investigate their battery performance. And then we perform the in situ or ex situ synchrotron techniques and also TEM and combined with the DFT calculations to deciphering the storage mechanisms. Here, I will introduce two representative work I have done. The first one is interface engineering of the transient metal characterized. We first use the hot injection method to prepare many kinds of the transient metal characterized, like the nickel selenites and nickel sulfates, and we can tune using this method to in a wide range for tuning their phase structure and the composition, and for like the nickel selenites from 0.5 to 1.5, and also the nickel sulfates, and then we can control their electrocatalytic properties like the hydroevolution and oxygen evolution like this. Because in the different structures, the transient metal have different valence states and local coordination environments. And then we can tune their composition from 0 to 100% continuously, and also the morphology and the structure of these materials. But here I will introduce the interface engineering in these materials because we believe that the interface density has potential influence toward their electrochemical properties. Here we use the successive ion injection that developed from the hot injection method. We injected the cationic precursors with different intervals and refluxing time and refluxing temperature to tune their interface density. And we can control their interface length from tens of nanometers to nanometers. And also we can obtain the atomic level interfaces. And then we use this method to prepare other kinds of interface structures, like the nickel selenides with different structures, and also nickel selenides and iron selenides. Therefore, this method is a general method for controlling the interface engineering. And then we investigate their electrocatalytic performance, like the oxygen evolution and oxygen reduction. And we find that with the increase of the interface density, their catalytic property can be enhanced. So one question is, what kind of trace metals contribute to the enhancement of the electrochemistry? Here we establish a model. The first box is the length of 1 meter, and then we cut into a smaller one with the length is half, and this we named N is 1, and then we further cut it into a smaller one, and we can obtain the 64 box, and we named it N is 2. And we can calculate that when N is 25 to 26, the length of the box is about 7 to 8 nanometers. This is similar with our results that we obtained in our experiments. And then the interface density has an exponential relationship with the N number. And we can speculate that if the depth of the surface can be activated with the depth of 1 nanometers, then the volume that be activated would be also the exponential relationship with the N number. And then we perform the hard XCS to characterize the valence states of the trace metals at different potentials. We can find that the nickel, both nickel and cobalt in the atomic level interface can be activated much easier, and at a relatively lower potential, the nickel can be more easily activated. This means that the nickel contribute more active sites at the initial stage of the electrocatalytic process. And then we calculated their molecular charge population by adding the different electric fields, and also we calculated their pathway of the OER, and then the situation is similar with the synchrotron techniques results. And this means that the interface engineering can enhance the activity of the trace metals in the interface composites. And here is the different activity of the nickel and the cobalt in different interface structures. And this is consistent with the DFT calculations. Another work is the disordered rock salt materials. So I will first introduce the background of the disordered rock salts briefly, because this is not similar with us. In these materials, the oxide and the fluorine occupy as the FCC structure, and the lithium and trace metals occupy the octahedral sites. And when charging, the lithium can transfer from the octahedral to next octahedral through the tetrahedral. But if there are trace metals facing the three faces surface of the tetrahedral, then we name it there trace metal channel. This is easy for the lithium transfer from here to there. But if there is one trace metal or even two trace metals around the tetrahedral, then the lithium transfer would face a higher barrier for the transportation. But if there is three trace metals in the three faces of the tetrahedral, then there is no channel for the lithium transfer. And we can imagine that if their transition metal can connect it one by one to form a percolation structure, then the lithium can transfer from this side to that side and to the other side when charging. And that is easily and with a lower barrier. So how to form the percolation structure? One calculation suggests that when the lithium excess is above 9%, then it can form the percolation structure. And these results are obtained from the Professor Seda's group at Berkeley University. And we also find that there is one property in the disordered rock source. There is at least one D0 transition metal in each of the disordered rock source. The D0 transition metal means that there is no electrons in the 3D or 4D orbitals, like the vanadium 5+, the titanium 4+, and the molybdenum 6+, like this. In this disordered rock source, we can see that the specific capacity and the specific energy are much higher than the traditional layered structures. But the capacity retention is much lower. Like for after 25 or for 50 cycles, the retention is only about 60 to like 70%, like this. So the stability is the biggest problem that facing in the disordered rock salt materials. But here we synthesized a new kind of disordered rock source, and we use manganese and chromium as transmetals. We use chromium 6+ oxides as the precursor, and the manganese 2+ as a precursor for bromelium, and for about 50 hours. And then we can find that there are many amorphous structures in these materials. This is very different with other disordered rock salts. And we also prepared other disordered rock salts like the manganese and molybdenum, manganese and niobium. We named it LMMOF and LMNOF. And here we compared with the LCOF. And we performed the PDF, the pair distribution function, to characterize their disorder degree. We can find that in the long range, all of them are disordered, but in the short range, especially in the first two peaks, the disorder degree of LMCOF is much higher than the other two counterparts. It means that the LMCOF has a higher disorder degree in the short range. And we also performed the hard access to characterize the valence states of the trace metals. We can find that the chromium was reduced to about 3+, and then the manganese was oxidized to about 3+. It means that there is no different trace metal in the LMCOF. And we performed the hard X at different bromelium stage, and we find that with the increase of the bromelium time, the valence states of chromium was reduced, and the manganese valence states was oxidized continuously. Then we tested the battery performance in both the half cells and the full cells at different current density, and from the current density from the 50 to 1000 milliamp per gram, the batteries can display long-term stability even after 1000 cycles. This is the first time to report the long stability of the disordered rock source. After 1000 cycles, the capacity retention is above 60%. And also the specific energy, the highest point is about 800. And even after 1,000 cycles, it is much higher than the traditional NMC 811 cathode materials. And also in the full cells that we tested also at different current density, the retention is also much better, and it is similar with the half cells. Then we have a question is what kind of transmetals contribute to the capacity? Then we perform the in situ hard access to characterize the valence states of the manganese and the chromium. We can observe that when charging, both the chromium and the manganese can be oxidized, and when discharging, both of them are reduced simultaneously. And then we determine the KH position and calculate the valence states, and then calculate their capacitor contribution from the transmetals and also the oxygen. And we find that the chromium and manganese contribute to about 80% capacity to the battery performance, and the last 20% may be contributed by the oxygen redox. And we also calculated the battery, the hard access of the LMNOF and LMMOF, and we can find that the manganese and the molybdenum has no change when charging or discharging. It means that the manganese and the chromium are the zero transmetals. They are only the skeleton of the materials and the charge capacitors, and they has no contribution to the capacity. So the capacity for the LMNOF and LMMOF are contributed by the manganese and the oxygen. The manganese contribution in the LMNOF is about 60%, and for the LMMOF is about 40%. But the last parts are contributed by the oxygen redox. And then we simply characterize the CV and to analyze the oxygen redox. We find that in the LMCOF, the transmetal redox stands at a higher voltage, but in the LMNOF and LMCMOF, the transmetal redox is occurred at a relatively lower voltage position. And then this peaks is contribute to the oxygen redox, and it is unreversible. But in the LMMOF, LMCOF, it is reversible very well. It means that for these two counterparts, the oxygen redox is not reversible, and it may has a bad release, and then causing the transmetal dissolution and also the surface densification. And we increased the voltage from 4.4 to 4.6 for the LMCOF. We also observed the oxygen redox that is unreversible for this one. So for the LMCOF at the voltage window of from 2 to 4.4, it is properly for this one, and it will not trigger the oxygen redox here. And then we perform the rigs, and we find that when increasing, when charging to a high volts to 4.4, the oxygen redox happened. But when discharging, the oxygen redox back to their previous occasion, and then we can also confirm that the oxygen redox is reversible very well in the LMCOF. And after 50 cycles, then we charging and discharging at different states, and from the soft access, we find that the oxygen redox cannot be triggered, and it means that there is no oxygen redox occurred in the battery performance of these materials. And also from the MWT images, we can also find that when training the environmental coordination of the transmetal in the atmosphere has been changed. But when discharging, it can revert back to their natural position. This means that the transmetal redox is also reversible very well. And here I will thanks to our group, or Professor Hu's group at Tianjin University, and Professor Lin's group at Virginia Tech, and Professor Andrew Rogach at CTU University of Hong Kong, and thanks to the testing center of Tianjin University, and also the Xuerong Center of Beijing, and the National Lab of Oak Ridge, SLAC, Argonne, and Brookhaven in the United States. And also thanks to the funding from the NSFC and other institutions. Okay, thank you.